We're very glad to have Juan Toscano visiting from Brown. He's a PhD student working with Professor George Kanidakis. And today I think he's going to talk about some of the recent progress in this group in physics for machine learning, especially its connection to some of the architecture accounts. And without further ado, please take it away.
Right. Thank you so much, first of all, Professor Ho and Michelle. Thank you so much for the invitation. It's really an honor to be able to give a talk here. So let's today, as Ishan was mentioning, I'm going to talk a little bit about GANs in physics-informed machine learning, some introduction, some of the extensions, and some practical applications. This talk will be organized like mainly in 4 parts. And in the first part, I'm going to talk about this physics-informed machine learning, like to give everybody like a general framework and some introduction of the method, and also some in how can we make it work better, like how to enhance it. Then we're going to go to a specific case study in which we're going to use GANs, in physics-informed GANs, to infer turbulent temperature fields from sparse velocity measurements. And in the third part, we're going to talk a little bit about this architecture that we recently proposed they are called Kürková-Kolmogorov-Arnold Networks, and which we're going to introduce it. And the last part, we're going to go into the learning dynamics of physics-informed machine learning, which we found that is agnostic of the representation rules, so it works for for MLP GAN. So for the first part, to start, like, what is physics-informed machine learning? Well, it's just an alternative to traditional numerical methods to solve partial differential equations. And we can see that there will be like 3 main components. One of them will be like a representation model, which will be a function that it's able to approximate the solution of a partial differential equation. We'll have like some governing equations, which would give us like the constraints that this solution should follow, which would be like physical laws, boundary conditions, and some data we have it. And an optimization process, which would be the way how we make sure that this representation model follows that rule. One of the interesting parts of physics-informed machine learning is that it's fairly simple to include data. And since they're easy to introduce data, they're quite strong, especially for inverse problems. So you can get them. You can obtain information for inverse problems quite easily. Now, how to improve PIMLs, because that's kind of like the general idea, and I think that we may know about it, but how to make it work, how to improve it, and then the answer to that would be like, we would have to tackle one of these 3 components. And that's what I'm going to talk right now. So for instance, like the first block, which will be the representation model. This is how it generally looks like. Like you will have some input and you will have some output. And we can do some type of input transformations. And like, for example, for the input transformation, we can try to introduce exact periodic boundary conditions, which will improve the accuracy. We could do feature expansions, which will also deal with the accuracy. We could do Fourier features, which is going to help us deal with the spectral bias. And then we see that we go to this somehow nested formulation. And in this nested formulation is common, and we may have heard, like, especially in deep MLPs, that we have this thing that is called vanishing gradients. So for example, we can use residual connections, which help us enhance the accuracy of the high order derivatives, they're quite important especially to enforce our PD. And each layer can be, actually in this case, I'm showing that it can be an MLP or it can be a CAN, but actually it can be almost anything. As long as differentiable, you can put whatever you want there. You can put a polynomial, you can put a radial basis function. And this is what we have like. Due to the maturity of the MLP, there are a lot of enhancements of the MLP that make them work a little bit better. Like, for example, we can do some weight normalization, which will accelerate convergence, and which is something similar to weight factorization. And we can add some adaptive activation functions, which will also help us with accuracy. And on the other hand, we will have some CANs, and I'm going to talk about CANs in the next slide. Now, the output transformations, they also help us like do other things. For example, we can do exact imposition of Dirichlet boundary conditions. We can do some type of constraint domain. For example, here we can make sure that this is positive. And we can add some complex constraints, for example, by making sure that this output transformation is the curl of a layer. For example, we can enforce divergence-free conditions. And that's what we get. Now, Kolmogorov-Arnold networks, that I said is one of the options that we have, is representation model. based on the Kolmogorov-Arnold representation theorem. It was proposed by CMX and Inferring, and it has many advantages. And I think that it's like a refreshing architecture, like it's quite new, it's novel. It has many advantages. For example, it's interpretable. You can use it and you can reconstruct some type of, find what is the symbolic expression of your PD, of the solution of your PDE. They generally require fewer parameters, which is good from one side, but it can also be some type of limitation, because sometimes there will be times when we need like really big networks to encode a lot of information, and then there will be some type of limitation. They're robust for catastrophic forgetting, which is common in MLPs, and they're robust to spectral bias, and they are robust to noise, which is quite interesting. One of the disadvantages of CANs, like the traditional CANs, the p-spline CANs, that's the one we are showing here. And we can here see how it works. Like each function will be represented as a linear combination of basis functions. This will be some b-splines, and it can be computationally expensive. But if some partial solution, you can change the basis and use some Chebyshev CANs or these efficient CANs, which use radial basis function, and you become maybe not as fast as an MLP, but with a speed comparable to MLP. Other small disadvantage is that somehow it deviates from CART, because it requires like some type of nested formulation, but it's not much of a big problem. Now, how to enhance if we want to go through the governing equations, and there will be like 3 points that we may want to tackle. One would be like the derivatives. To give an idea, the traditional way is we use the automatic differentiation, which we obtain the derivative using the chain rule. But as I mentioned here, one of the disadvantages is that like if this is too deep, if you have too many layers, here you will have these vanishing gradients. You can use finite differences, which makes it a bit faster, but then again, you are constrained to the grid. And then you can also do it some type of modal prediction, which brings some advantages, but also means that you will have another soft constraint, so it will not be exactly the true value. Now, regarding the physical laws, there are some things that you can do. Like, for example, here, you'll see that you will get the solution of your model, and then you will see, since this is differentiable by any of these methods, you will be able to construct your boundary operator or your PD operator, like your ODE operator, which can be fractional, stochastic, or it can also be, so for multiple solutions, quite flexible. And then you will have some forcing term that can be known or unknown. And yeah. So one ways that you improve this part would be, for example, with non-dimensionalization. This is quite important, for example, for convergence. If you don't non-dimensionalize it, there will be many times where your model will not converge. You can reformulate it. For example, in this case, we see that it's like we're using the vorticity formulation. And one of the reasons will be because now we have one less output, and we don't have to predict pressure. And another way would be, for example, this approximation. And one of the main advantages of this approximation is, like, for example, in this case, if we get like a linear problem. And for linear problem, there's a paper that shows that, theoretically shows that if your loss goes low enough, is small enough, then you are close to the true solution. That's a paper by Mario Seinhofer. It should be the reference here, but I don't know where it is. Okay, never mind. Okay, now that you have your physical laws, you rewrite them in form of the residuals, which will be like, you just compute the pointwise errors of all of them. And then it can go either in the strong form, which will be the normal ping, or you can go into the weak form, which will be the variational ping. And there are many options, many ways of doing the variational ping. Now, through the optimization process, the governing equations are represented as an optimization problem. The idea is like we will want this approximation to be as close as possible to the true solution, and we will do it by minimizing some constraints. And this is what we call like the optimization, the physics information learning problem. Like, for example, if you have multiple constraints or complex constraints, you can try doing something like sequential training. If you have like a really complex domain, you can try to do some type of domain decomposition, which means like now in each one of these small subdomains, you're going to have a specific neural network. And ideally, you want to solve this in the whole domain. So you discretize it in this way, which somehow resembles of for example, if this is randomly sampled, it resembles of weighted Monte Carlo. And then we will have like some components, like these global weights will be in charge of balancing each one of our loss terms, and these ones that will go inside will balance the loss terms. And this is what we call local weights. For example, here for Allen, you see that this will help us will help our model like focus where we need. So that will make the problems a bit easier. And also we can do some type of sampling method, which is essentially the same thing. The only difference, like we're going to put more points where the residuals are high. Again, similar to when you do importance sampling. Then you go to the optimizer, and the way we usually do it is like in some form of gradient descent. And you can see that this is actually quite flexible, this formulation, because, for example, if this HK is equal to the identity matrix, then you fall into first order optimizers. And if you play with this alpha and then you make it like the momentum term, then you will get like Adam. And when you approximate this HK to the Hessian, then it will be like the LBFGS, and it's a true Hessian, and you will get the Newton method. And there are many other studies that have tried to improve the method and have developed specific optimizers for ping, and I encourage you to check them if you are interested. Okay, now one of the main components will be like when we formulate this loss function, and then we do it like, for example, with these local weights, and this is like what we call RBA. And the idea of the RBA would be like we will assign local points to each one of our points inside our domain. For example, what we see in this first plot will be the residuals of our equation while we're training. And what we see below would be these multipliers. And you see how they evolve at the same time. And for example, if I may stop here, if the code lets me, if me go a little bit farther here, for example, you see that if you take the mean here, you would see that these four corners will be most likely ignored for the optimizer because everywhere else is almost zero. So when you try to compute the mean will be really small, so the optimizer will not care about minimizing these points. But the RBA will make sure that we'll give more weight there, so make sure that it will be like some kind of an attention mechanism to make sure that the optimizer gets the information. Here we'll have like the prediction at different time. This is for Helmholtz equation with a 6x6 wave number. And this will be the weights, how to look at some specific iteration. One of the advantages of this RBA is like they are bounded, and they go from 0 to 1 to the minus with this parameter, the hyperparameters. One extension of the RBA that we recently proposed in these KKAN papers is like we call self-scale RBA, which is a global and local scheme. And the idea will be like we're going to adjust this upper bound of the RBA to make sure that as we move forward in training, that our model always keeps learning. So we can have like extended training for like a lot of iteration. And with it, means that we can keep reducing the error. And one of interesting part, like for example, for these global weights, because if we recall, this is our expression, like let's say for the first order, assuming like this would be a first order optimizer. This is how would you do the gradient descent. And the idea would be that in this case, what you want to scale would be the gradients of each one of the loss terms. And the idea maybe in this picture looks a bit better. Like you see that if these gradients are not scaled, maybe the overall direction, the overall update direction will be in this part. But if they are scaled properly, the overall direction would minimize all the losses at the same time. So the way you choose these weights would be like in this way, iteratively, we would choose like this way. You see that this would be normal, some type of normalization. Then the norm of each one of the gradients will be 1. So then you are making sure that all your weights, all your directions are properly scaled. So you're minimizing all your constraints.
Sorry, could you please explain a little bit more what does the first K Kürková here mean?
Oh yeah, sure. Actually, for the KKANs, I'm going to go into the third part of the talk. But yeah, we propose it in these KKANs. Okay. But I'm going to talk about that in a few minutes. Yeah. Now, as a case study, like now we're going to see how to use all the tricks that I mentioned to solve some kind of real problem. This is like solving turbulent flow from real data. And it's like we have this complex domain. We have like more than 5 million points. And okay, so this is also from another study. And just a brief introduction, why do we care about that? Well, first, this is what, if you ask ChatGPT to give you an image why turbulence is important, and you see that it gives you this. So even ChatGPT knows that turbulence is everywhere. It has like in climate modeling, in our airplanes, even in space, in our turbines, turbulence is everywhere. And it's considered like the last frontier of physics because it's not fully resolved. Yeah. But well, there are several approaches that you can tackle turbulence, like one of these theoretical approaches which describe the overall behavior, but are limited to idealized formulations. You have like numerical solutions which are quite accurate, especially if you go to DNS, but DNS is extremely expensive. You can have like experimental methods. We can capture the real world physics somehow, but they are limited to this resolution and potential noise. And also, for example, the simultaneous measurement of velocity and temperature, everything sometimes is challenging and cannot be made. And also from there, you cannot derive gradients or other quantities of interest. And you can also do it with deep learning approaches, but we all know that deep learning models are like some kind of black box, that they are not so much informative. So the idea would be to use this physics information learning framework that I introduced in the previous slides to try to combine the best of all these approaches, all right? So now let's talk a little bit about the experimental data that we have. I said we have experimental data. We'll have like, this is for the Rayleigh-Bénard problem. This is turbulent. You see that the Rayleigh numbers in 10 million, 3.4 times 10 to the 7. Prandtl number is 10.6. And then we'll have like this Rayleigh-Bénard cell, which will be this part, like the transparent section. And we will be able to capture simultaneous measurement of temperature and velocity in this yellow subdomain using some cameras and some nice tricks. The way we get the temperature is like, well, this is a study by our collaborators before or work with them. They added these thermochromic liquid crystals that have something really nice property, that these crystals change color as you increase the temperature. So you can use them to track your particles, and with that you get velocities. And also based on the change of color, you can get what is the temperature. So which is quite interesting, right? So from the particle tracks, you use Lagrangian particle tracking, and you get the 3D components of the velocity in time. And then you can create a map by a calibration of the color to the temperature. Yeah, there are some limitations. For example, the temperature resolution of these crystals is not like into the full spectrum of this. You can only do it for sparse measurements. Even though you have a lot of points, it's still sparse. It requires some complex calibration, which means that it's prone to noise, and it cannot resolve the boundaries, because near the boundaries, your temperature will be either really high or really low, and then it goes out of the sensitivity of your sensors, and so you're not able to resolve that. So a goal would be trying to use these physics-informed machine learning methods to getting from velocity, which is somehow easier to access information, to get some type of temperature. So that's what we're trying to do. Now, how to put it in the framework that I just introduced. Now, for the representation model, we're going to use this CPCAN. The CPCAN, CAN stands for CAN. DC stands for Chebyshev polynomials, and PCAN stands for physics informed. So it's a physics informed CAN that use Chebyshev polynomials as basis functions. And why do we use this? Because as I mentioned before, they require fewer parameters, and they work quite well for noisy data. And this will be how the neural network that we're using looks like. Now, for the equations and the governing equation or constraints. Oh, what happened here? Sorry, I think. Yeah, now it works. I think I stepped on the. Oh, it said that I stop sharing. Let me go back. Maybe here. Yeah, sorry about that. Yeah, so the idea is like we will have some partial boundary conditions. We know that we have like the walls, the up and down will be cold and warm. And we know, remember that we only have information in this green domain. We don't have information of the side boundaries. So that's why we cannot do it with traditional numerical methods straightly. And we're going to use the Rayleigh-Bénard, but in the vorticity formulation. Why? Because in this case, we're interested in the temperature. We don't care that much about pressure. So if we write in the vorticity formulation, we can have only one unknown. If we have two unknowns, it would be quite hard to get both at the same time. You see how this problem becomes hard because we actually only have partial information of the velocity. We don't know much about the vorticity. We can get it somehow from the velocity, but we don't actually get it. And we don't have information on the temperature. So that's why it would be hard to do it with traditional numerical methods. Now, for this case, we're going to use a problem. Remember that I said that we can formulate this form as a problem, and we're going to use a sequential training approach. And here's like how the loss and the error looks like. What we have on the left will be like the training errors, and then you can see that in the first stage of training, we're going to feed only the velocity data and some theoretical model of that rules how the temperature should work on average. Right? So then you can see that both of them decrease, but if you check the equations loss is quite high. So the errors look good, but they are not following the PDF. In the second stage, we're going to somehow apply the partial physics. And when I say partial physics, it's like I said that, remember that I said that we have like this Rayleigh number. This Rayleigh number is quite high. So we're going to use a smaller Rayleigh number. We use a smaller Rayleigh number, so our model is able to capture like the general diffusive behavior. So without, and once we get that, we get to the full model what I have here. Once we train it for long enough, now we can do another trick that is switching like the L2 to L1. And the reason is quite intuitive. Like as you go smaller in training, as your training loss becomes small, if you have a small value and you square it, that value becomes even smaller. So it's really hard to optimize. So if you're small, you change to L1, so you only use absolute value, and then it becomes easier to optimize. And also we use for the local weights, we use the RBA that I just introduced, but we add another trick that is called with R, which will be the resampling. And what does it mean with resampling? Like based on the story of the RBA, remember the RBA are just accumulated residual. So it tells us already on average, where are going to be the higher regions. So we can use them, we can reuse them to sample. So if we compute a PDF from our RBAs, then we can use that PDF to sample points. And how it looks like, maybe this picture looks like a bit better. This is for a 2D case because it will be hard to see it in a 3D case, but this is for a 2D case, a steady 2D case to see what happens. So you see, you have the RBAs become red in some regions, but you're also resampling them more often. So it's like you're tackling the problem for two fronts. You're sampling more often, and you're also assigning like a higher weight. Yeah. So once we have that, we can get this type of velocity reconstructions. Like this will be like the 3D velocity data, and this will be what we reconstruct. What we have here will be like the PDFs in the testing data set. We test in the 50% of the data, which means we only use 50% of the data to train, and we test in the other 51. And this will be the PDFs on the testing or the validation data set. And you see that the distribution looks quite well. And also we have a error on the validation data set that is around like 10%. Additionally, we can also compute the average velocities. And what we have here in blue points will be the experimental data. And what we have in red will be like the prediction of the model. You have a question, Ishan? Yeah, sure. Sorry. Yes.
First is, see here you sort of put the boundary condition loss together with a data instead of together with equations. So in first stage, you fit not only your data, but you also put boundary condition. I was just wondering, are there like any intuition why you separate the boundary condition of the equation with the
I think that if we if we think about it, like the boundary conditions can also, yes, they're clear. Yeah, but if we think, we can also think the boundary conditions as data. Huh? Yeah, that was actually what I was mentioning before. We use hard constraints. If you use hard constraints, I'm going to show you that we are not also able to reconstruct the fields, but we also get to the turbulent statistics. And then the interesting part is like, if you use hard constraints, you get the velocity field, but you don't get the statistics. So that's why I said that with hard constraints, actually we were talking about that yesterday. With hard constraints, you have to be careful, because if you have enough information to constrain your model, then you're good. But if you're not, then maybe you may not be in the right place. That.
Another question, final stage.
Yeah.
You switch from L2 to L1.
Yes.
But this seems a bit, to me, you mentioned in the beginning that if you have the losses, if you just have an L2 loss and you have certain small region, if you use L2 loss, it sort of gets average out. But if you're using an L1 loss, it's getting even more average out, right? So if you want to make sure that your residual loss is sort of small throughout the whole domain, you probably want to use a higher LPP loss. Does this make sense?
Well, the problem is like that makes sense. Yes, it makes sense. But the problem is like we should think that we are training in single precision. So when we become too small, then yeah.
Because I was thinking use L2 squared or LP to power.
Yeah, I think that would be possible. Actually, this is a strategy that's switching from L2 to L1. There's a type of laws that they develop for normal deep learning that is called Gruber laws, which they do that, but it's somehow automatically. Like once you go under a threshold, you switch to L1. When you're above a threshold, you're in L2. So that's kind of like the intuition of what we were doing this. But yeah, but I'm sure that there will be another alternative that may also work as well.
Maybe I have a follow-up question. So looking like here, when you switch from L2 to L1, you jump from one local minima to another local minima.
Yeah.
So that seems to indicate that because the landscape of L2 and the landscape of L1 is different. So when you switch to L1, you, for some reason, find a better local minima.
Yeah.
That's giving you a lower L1 errors.
Yeah.
Yeah, that's very interesting. If you guys are able to visualize
the
thing and see how it jump from one local minima to another, that would be very interesting.
Yeah. That actually, I didn't play with the loss landscape, but it would be nice to see them. Yeah. Does anybody else have a question? Okay, then I will keep going. Okay, so then with that we see that we reconstruct. They do not only match. They match the PDFs. They match it in L2 because the relative error is 10%, and they also match in average. We can also do, and here's like how the reconstructions look, and will be prediction, measure, prediction, and error, point-wise errors. This would be like the temperature inference. Again, we validate the model, and it's 100% of data. The model did have no information about temperature to make these predictions. And the interesting thing is that we get a relative error around 3.5%, which is quite small. And also, and here, like, we can also compute the convective heat transfer, and we see that they also match, and the PDFs also match. Maybe the tails are you miss a little bit of the tails, but if you see that you only just sprinkle a little bit of data, then you actually match the tails. Also, another thing about the limitations of the actual experimental data, for example, let me try to write it if I can. Yeah, I don't know. Okay, it doesn't let me write. No, it doesn't let me write. Sorry. Okay, I try. It would be like you see here this jump. It's because this is the sensitivity of the sensors. So the sensors cannot get less than 0.4. So do you see that here how this distribution gets stuck there? Yeah. So another thing that what you can do is like you can also try to plot the average temperature, and then you see something quite interesting. As I mentioned at the beginning, the experimental data cannot capture the boundary layers because it goes out of the sensitivity of the sensors. So we know that next to the boundaries, we cannot trust the experimental data, but in the middle, we do. And then we see that next to the boundaries, the model follows partially, especially the one above, follows the theoretical model, but the data does not. And in the middle, it follows quite close to the experimental data. And on the bottom, also that same is true. Also here we can compute the boundary thickness, the boundary layer thickness. There's also turbulent photos can be in a study, so we have some models for that. And then you see that actually we can capture the boundary layer thickness is like exactly the transition is exactly in that point. And well, not exactly, but around that point, especially for the cold boundary layer, not so much for the hot boundary layer. These are would be the point-wise predictions. In terms of the velocity, we can also get these root mean square fluctuations for both cases, and then you see that the peak of the square root fluctuations will be captured almost around where the theoretical model tells us there should be the viscous boundary layer and the thermal boundary layer. So this model is able to capture all these things, even though it has no information about that. Additionally, since this is representation models, this is a function. So it's a function, and it's a continuous function, and it's a differentiable function. So we can get derived quantities. For example, we can get like the vorticities. We can get the convective heat transfer, but also we can get the thermal dissipation rate and the viscous dissipation rate, which the definition is described here. And so we are able to obtain quantities that usually they are limited to DNS modeling. So this is what we get here. Also, we can get a little bit farther with the gradient-based statistics, and then we can compute the QR distribution, and then we get like this kind of like representative or common inverted teardrop shape that is common for turbulence. And then you see that it follows also the I don't remember, is Billy Coe's tail. That is the one we're showing in black. And this will be like the tensor invariance. And we see that we get it. And we have like quite a good agreement with the experimental data. Also, we can try to get some PDFs of the thermal dissipation rate. And again, you see that we get good general overall picture. There are some low probability events that we may not be able to capture straight away because the neural net will try to smooth things out a little bit. But if we add just a little bit of data, just 5% of data, we're going to be able to get this low probability events. And that's the part of yes.
5% compared to how many data you use.
Before the one on the left is no data.
But I saw doing a training plot, you first train on the data.
Velocity data.
Oh.
Yeah. The temperature the model never sees. And actually for the velocity, you use 50%, I think, is here. Velocity data. But for the model, you don't use any temperature information. Yeah. Okay. So this would be like some summary about the ABT. Do you have any questions about this part so far? Okay, maybe if there are no questions, maybe I can go to the, well, in general, it's a brief summary. We can reconstruct differentiable velocity temperature fields from sparse velocity data using and methods like CP, CANs plus RBAR, and sequential training. We validate our model with unique 3D Rayleigh linear convection data, and then we'll achieve DNS level accuracy with good agreement with experimental observations. And the inferred observations align with the theoretical and experimental results from previous studies. Now, for the last part, second to last part of this talk, I'm going to talk a little bit about this architecture that is called Kürková-Kolmogorov-Arnold Networks that we put an archive a few, maybe weeks ago, last week actually. But this will be a joint collaboration with Lilian Wang from Nanyang Technological University in Singapore. And well, okay, let's go in there. So this is it. Let's recall that KKANs are based on the Kolmogorov-Arnold representation theorem, which tells you that if you have any multivariate function, you can be expressed as the summation of univariate functions in some kind of combination, right? This univariate function, and the nice thing about this expression is that like it's an exact representation, so it's not an approximation as usually the expression of the MLP, and that was actually pointed out in Ximing and Yishuan's paper, so it's quite nice. But could be some problem, and the problem is like these univariate functions can be non-smooth or can even be fractal, which essentially means that they may not be learnable. Due to this, let's say that this fact, there have been like two main lines of research in the CART research. One would be like construction of refined version, and to refined versions that mainly they try to reduce the number of univariate functions, and also try to play with different smoothness conditions, like would be like more into the theoretical part. And another part would be like trying to apply this theory to deep learning and general machine learning. And one of the ways to apply this CART to machine learning is using KKANs, that was proposed by Ximing and Yishuan, but also in 1987 there's another type of application by Nielsen that's called Kolmogorov's mapping neural network, and here we have like several variations, but they have each one of them have like their own properties. During this research, this time there was some kind of debate, and there were some pessimistic perspective and optimistic perspectives that can be actually observed from the name. You see that the first name says CART is irrelevant, and the second one says CART is relevant. So it was like some kind of back and forth. But the pessimistic perspectives are here. We can see that they say that essentially they say that we cannot learn this hopeless to make it like trainable, and this was mainly defended by Tommaso Poggio and Girossi in this paper. But there were also some kind of optimistic perspectives, especially by Kürková, who said that maybe it's true that if you try to go to exact approximation, you can have this problem that can be fractal, non-smooth, and maybe not being learnable. But if you sacrifice a little bit of exactness and you go to approximation, then you can do quite nice things with the Kolmogorov-Arnold representation theorem. And also, by the way, I invite you here. There's a YouTube link, and there's a talk by Ximing. He also did like a bit more extensive analysis of the history of KKANs and this kind of interesting debate. So, okay, so based on this optimistic perspective is what we're trying to aim. So this does the KKAN stand for Kürková, which means we're not aiming for exactness, but we're aiming for an approximation. And well, the Kürková approximation theorem says something along these lines. It's the same KAN, but it's here you see you don't have the 2D plus 1, but you have an M, which should be greater or equal to 2D plus 1. And then they say that this univariate function can be like approximated by this kind of a stairwise function. This is like a sigmoid function. And you see actually quite interesting that if you put here a sigmoid function and you plug it in here, you get a 2-layer neural network. So that's how both are connected somehow. Okay, yeah. Then so what was our contribution? Somehow like we extended this theorem to other univariate functions. We can use other kind of things like radial basis functions. We can use MLPs. We can use orthogonal polynomials for any function that can be a universal approximator. And that's what we try to do. So okay, so now what do we do? Like this is like how the architecture of this KKAN looks like. It would be like a 2-block architecture. Like the inner blocks will be try to approximate the inner functions, which will be this part that we have inside this G. And the outer functions will be what we would trying to approximate the outside, the outer function. One thing is like, it's been known that maybe one of the hardest parts to learn in this Kürková in these Carrot representations are the inner functions. They are the ones that are harder to learn. They are the ones that can go crazy because they say that there's a connection. You can actually make some type of connections and assumptions of the outer functions based of the function that you're trying to approximate. But for the inner functions, they can be whatever they want. So since that's true, we decide to use a multi-layer perceptron for the inner blocks. Why? Because it's widely developed and it's quite strong. We know how to do a lot of things with MLPs. There are a lot of optimization methods for MLPs, so that's why we can use it as inner functions easily. And for the outer function, we can use the linear combinations of basis functions as similar as they did in the original KAN paper. Now, to go a little bit in depth in what each one of those, for example, in the inner block, we actually are going to use a slightly modified MLP that we call it enhanced-based MLP. And the general idea is based on this paper that is called Adaptive Basis Viewpoint. And actually in the review, it's detailed that this adaptive basis viewpoint is not from us. But the interesting thing is like if you see, let's say this is just a 2-layer network, you see that if you rewrite this in a different way, and then just say that you call all of this like this phi of x, then you see that you fall again into a linear combination of basis functions. So you can think as an MLP a way that you're going to feed an input, and that input is going to give you a suitable basis, and then the last linear layer just is going to combine everything. So that's kind of like the general idea. So the idea is like we can enhance this. If this will be true, and this is intuitively true, and in the paper they go a little bit into the theory actually too, we can enhance this representation by using orthogonal polynomials. So because now, if for example, if we add a Chebyshev layer in the end, we'll make sure that we'll have some kind of orthogonal groups. Not all the expansion will be, there will not be orthogonal all the points, but we'll have orthogonal groups. And then that's how we can enhance its representation capabilities. For the outer block, like the outer functions, we can use the again linear combination of basis functions as they did in the first papers, and we can use different options like radial basis functions, orthogonal polynomials, splines or sine series. This is we were using like this basis from Acknowledgements, which was another paper on KANs that they were trying to use another version of the Kolmogorov-Arnold representation theorem, not the original one. And well, this will be like the results that we have. First, we're gonna try with some function approximation, and we're going to try a highly discontinuous function. We can see it here that we actually have that two big discontinuities along this t equals 0 and x equals to 0. And this is also, you have some kind of high frequencies because you have like, well, kind of you go up to 4, so maybe not that high, but it goes and you can go to high frequencies. And then we see that actually in this case, KKANs perform a bit better than MLP and also in the secant, which would be the normal KANs with Chebyshev polynomials. And if we compare the relative error of the evolution, we see that we can go a little bit lower.
What's the intuition why it's better?
Like
what's the intuition why KKAN is better?
In this case, maybe it's what I was saying, like if you go to the discontinuous function, maybe like the expected inner functions maybe go a little bit crazy. So if you have an MLP, the MLP will be a bit more stable, more.
I see. Worse compared.
Yes.
But here, for example, the rabbi, that's a secant. Like you see in the training dynamics, it seems that after 10 iterations, it just stopped. Or like, it's not even a search, it just stopped learning.
Yeah. Actually, some of the intuition for that. Okay, first let me introduce you about this training dynamics. Is they called the geometric complexity. To the left?
On the box, the rabbi, it's a secant.
Yeah.
After like 10 iterations, the law function plan.
Yeah, so most likely is that you got stuck in a local minima, right? So you cannot escape from there. Yeah. Okay. Then what we're showing on the right is the geometric complexity, and the geometric complexity is nothing more like is the discrete Dirichlet energy, and the idea it kind of tells you like the representation capabilities of a model, and it's had been linked. For example, the good initialization schemes usually have like a low geometric complexity, and the reason an intuitive reason can be obtained from the learning dynamics, which I'm going to talk in the last part of this talk. But the idea is like, if you go too high, then you may be overfitting. So maybe what we can observe here is like secants are their geometric complexity is a bit high, which may indicate that secants are doing a good job, but they are overfitting to the training data. So that may be what is happening.
Oh, so this is for testing.
Yeah, this is the relative L2 and testing data.
I see. Then if what will happen if we increase your training data, then overfitting becomes a good thing, right?
Yeah.
Okay, I see.
That will be.
So in that sense, that means KCAN is less expressive than CCAN. Is what we are saying, like CCAN is overfitting to training data?
I would not say that if KCANs are less expressive, I'm not sure if that will be saying, because in this case, you are going, if you think, I just said that is the Dirichlet energy, right? So it will be the derivatives respect to your input. So what it means that the derivatives with respect to your input, if your function is unique, the derivatives should also be unique. And then actually in this case, you may not be able to see it, but you see that in all the cases that work, well, because there are some cases in the three of them work, you will see that all of them converge to the same value. So it essentially means like there's an optimal geometric complexity. So in the end, it's not like it's less expressive. It's like there's a unique. So what this indicates is like maybe secants are giving you a model that is overly complicated. That's what it's saying. Okay.
That's also the same.
Yeah, they all of them have around the same number of parameters. Yeah. Now we go to another part that would be we also tried for physics information learning using all the things that I mentioned before. Actually here making a comparison is a bit hard because, as I said, MLP is quite mature, so there are a lot of tricks that we have for MLP to make it work well. For CANs are quite new, so we don't know that much what is the optimal initialization scheme. We don't know exactly how to make it to extend the full potential of CANs. Right. So in the first stage, what I'm doing is like we're comparing just vanilla models. You see that we tried somehow to match the number of parameters. Here's what you see the number of parameters. Here we can see the time iteration with training like with batch size of 10,000. And you see that if the batch size is small, actually the training time of the three models are essentially the same. So you don't have the problem. And then you see that if you compare the relative error, in this case, we don't have any trick here. You see that actually secants and KCANs do a really good job, and secants actually is slightly better than KCAN. Okay, when you don't add any tricks. If you add some more tricks, which this called is self-scale RBA, which was the last part of the RBA that I introduced today, with this resampling, again, we somehow match the number of parameters. We see that that actually you can go with KCANs, you can go to 10 to the minus 5, which is quite good. Let's recall that in single precision, the lowest you can go is like 1 to the minus 5. You go if you are to the minus 6, you're extremely lucky in single precision. So you're almost bordering that part. One disclaimer here that is important and is also mentioned in the paper was like for the MLP and for KCAN, we're using random Fourier feature embeddings. So what essentially means is like we can but for the secant we're using modified MLP. Yeah, the modified MLP is an improved MLP. That let's call it that way. And we said we can use that both for MLP and for KKAN, but we cannot use it for CKAN. So which essentially is promising because it means that if we manage to get some kind of analogs of all these kind of nice methods to CKANs, we may be able to reduce the error a bit further because they don't have that much improvement, that many adaptations. The error is quite good, right? Now, as well, like the second part, and we use RBAR, and you see the time is some kind of comparative, and actually they are a bit faster because they are not using this modified MLP because they cannot. You can try to actually do like a 1-1 copy, like try to enforce the modified MLP architecture, but it doesn't work for KKANs, unfortunately, for CKANs, unfortunately. Okay, and for the third part, we're going to compare a fully optimized MLP. Like we put it to the MLP, all the things that we know would work for the MLP, and we're gonna go as close as the error as small as we can. Again, we can do it for the KKAN because the inner functions are MLPs. And well, this will be like the training dynamics before I go there. Sorry about that. And something interesting happens. You see that actually the MLP converges around like 30,000 iterations, but CKANs and KKANs converge almost immediately, almost like 2,000. You start to converge, and it's quite a good performance. This is what I was mentioning before. Like when you have the right model, all of them converge to the same geometric complexity because it's a unique function. Yeah. Okay. Now let's go to the next part, which will be the and you see also that the self-scale RBA actually they improve the performance of all the models. Now, when you go to a bigger networks, so when you increase the number of parameters to what is on the state of the art, and there are a lot of papers where they have done this, you can see that actually, if you do that, actually for CKANs, the time it increases. Before it was like comparable, but if you have too many parameters and you use full batch, actually they become too slow. But not too slow, but comparatively slow with CKANs. Then we see that if we do all the tricks with MLP plus SRBA, we get to 3.5 to the -5. But with KKANs, we're able to get to 3.07 to the -5. But remember that I said that with KKANs, we have like these special types of RBA that let you learn for longer. So if we train it for longer, we see that we can get all the way down to 2.56 to the -5, which is quite competitive with the current states of the art, which is this BRDR, which is by Panos Tines from Pacific Northwest National Lab, is 1.4 to the -5. And that's what you can do. So this model is quite competitive to the current state of the art models. These have some 3 implementations of KAN for Allen KAN. And these are like the results that they gotten from this paper. In the original KAN paper, there was not, that's why I not referenced this example. I did not reference this example. Okay, then we go to the operator learning. So we can do that too for depot nets and for QR depot nets. And we see something quite interesting again. And okay, then we're gonna do it for Borger's equation. We're going to have these boundary conditions, and we're going to sample the initial condition from a Gaussian random field, as in previous studies, and this like CFAN study and also the FNO study. And these are like the results that we are trying to get. First of all, you see that if we compare like this left part of the panel, we see that actually KKANs achieve a better performance, but CKAN converge a bit faster. So, which is something important to mention. But you see that when you do this QR depot net with the two-stage training, which is like an enhancement and optimization for depot nets, is that it improves the performance of all the models, but it does not improve the performance of CKANs, which indicates that maybe this architecture is sensitive because again, it's a bit disruptive, so it's kind of hard to apply all these tricks. And this would be an example for 3 representative cases. And in summary, I'm going to jump this a little bit because I have the last part. Sorry, I think I took too much time. Another thing that we can try to do is like learning dynamics, which would be how the neural networks learn using the information bottleneck theory. And we find that the learning dynamics are common to all representation models. Again, this is with another study. And the learning dynamics via the information bottleneck theory, this tells us like the deep learning algorithm extract relevant information of the input with respect to the outputs. This was proposed by Tishby, and there are many studies that have gone to there. And one way that you can measure it is using this signal to noise ratio. And what this does, maybe we can see it a little bit more in this animation. And the idea is like, what we are observing in the first row would be the prediction, the residuals, and the lambdas, which would be the weights that I mentioned before. And this would be the errors at each one of the iterations. And we can observe something, and I'm going to go like this. You see at the first stage, this is where the model is kind of fitting like the general pattern. In this case, it's characterized by the high to low SNR. Then we go to, but every time that the model gets a good pattern, for example, here, it knows that there should be some kind of division here, the SNR jumps and the relative error decreases a little bit. And when it jumps the second time, is when the model gets like the general picture, and then is when it's learning. I'm gonna go a little bit in detail what each one of these stages means and what we can get from there in a few seconds. Okay, so the general idea is like every time we have a jump in the SNR, the relative error decreases. Okay, so what are these SNR and what are these stages of training? The SNR is tells us like some kind of relation between an ideal gradient that minimizes the error in all the subdomains against some kind of a standard deviation against some noise. So it would be like the signal would be like the ideal gradient, and the perturbation would be how away from the ideal gradients are the specific gradient on which is one of the subdomains. This we can observe these three phases. In the first phase, the fitting phase, you see that the first stage, the SNR is high, and the reason is clear because at the start of training, the error everywhere is high. So it's easy to get into an agreement. So the SNR is high. But as you keep learning, as you go, you reach a point where the SNR decreases. In this case, it's like you don't have an agreement between the subdomains. Ones will try to move you to the right, others to the left, others up, down. So then you have like this exploratory phase. Then there is a point where, and this is called the transition phase. Then once the directions of all these subdomains get into an agreement, you go to this diffusion stage, is where your SNR increases, which means all the common direction is clear. And then is mainly when the relative error decreases. Yeah, what are the practical implications of this? One of them is like, you can make like a clear link between the SNR and convergence. That means that when you are in the diffusion stage, or like the third stage is when you have like the main convergence of your models. And this is true for all the representation models. And here is two examples. For example, we have Allen-Kane and Helmholtz. And as I said, like the earlier you go to this high SNR, the better performance, because it means you go to the better agreement sooner. And earlier diffusion usually implies better performance. And also something interesting, and I'm not showing here, but the models that will never learn, there are models that we're going to get trapped in this transition stage, which means that the model will keep in this exploration stage. Well, they will never get into an agreement where is the right direction to go. This is a general trend, and this is true for a lot of physics for problems have Allen-Kane, Helmholtz, Borgers, and cavity. We see this kind of trend. We can also observe, like what I was mentioning before, that every time that you have the jump, the SNR improves. This is for a real case. This is an inverse. This is a flow inside a mice that is alive, and you're trying to solve an inverse problem. You have 12 loss terms, and then you can see that you have actually multiple SNRs. And every time the SNR jumps, you get a better picture of the problem. So in this case, you see you're getting like the general picture, then you get you're getting the data, then you're getting the boundaries, and then you can complete learning. And every time you jump, you see that the relative error decreases. Another practical information about this would be like you can get some kind of information compression, because remember that the information bottleneck theory tells us that in the end of training, your model becomes efficient and the representation gets simplified, and then you get to this kind of like nice stage, like where and then you can see it here, like where the mutual information decreases, means that you're only capturing the relevant points. And I'm trying to go a bit fast because I have 3 minutes, sorry about that. And another thing that is quite interesting is like this binarization that we observe. Like in the first stage, like this will be in the transition. You see that if you plot the activation functions, like the output of all your neurons, you see that you have like kind of discrete, this continuous information. Like you see that you can go from 0 to 1 everywhere. But in the last stage, when your model becomes efficient, you don't need actually the full spectrum to get information. Actually, this becomes binary in the end. So your model becomes efficient. At this stage of training, the information that is only going is like would be ones and zeros, would be like which is quite interesting. Another implication would be there's a close relationship with the geometric complexity. This is geometric complexity. How is it defined? It's just like I said, like the Dirichlet energy, just take the gradient with respect to your inputs and then take the Frobenius norm. And it can be linked to the generalization capabilities. It can be linked to the SNR. You see that fits in, you start with low geometric complexity. You see that's true for all the cases. And then as you are in this stage, the complexity increases. So your model becomes complex and complex and complex until it's able to learn to be as complex as it needs to be able to give you information about the model. And then in the last stage, the model simplifies representations, and then you see that how the complexity, in this case, you're overfitting a little bit, but in diffusion, you start to fit to the actual data in the way you should. You can get another things, like, for example, this is, for example, the discontinuous function information that I was mentioning before. You see that when the SNR decreases to this ideal SNR, to this good value, you see that's when your loss flattens. So you know now when to stop. Let me go to the next slide. Yeah. Also, for example, in this case, this is for Alencon, and this one will be the fully optimized MLP. We'd have like this modified MLP and for random Fourier features. And then you see that this actually increases the initial lower complexity. And then what happens is, like, if you have an initial lower complexity, initial geometric complexity, the model first has to simplify the representations before increasing again. So that may be, and give us an intuition why is preferred models with initial lower complexity and why the good initialization schemes usually have initial lower complexity. In which one?
The one you highlighted.
Yeah. So then it means that you have to reduce first, right? That's what the point was, right? Yeah, but this model is too complex. Yeah, but I'm not saying this is good. I'm saying this is bad.
But this is the state of the art.
This is the state of the art. Yeah, but you first simplified. Yeah. Yeah. Yeah, you first simplified. Yeah. Okay. And actually, the thing that I was saying about the initial complexity, I actually that's in the original study where they proposed the geometric complexity, they found it for all these problems. Also for the operator learning is, again, notice that when the SNR decreases and when the loss flattens, and then will be some acknowledgement to my current group, Professor Karnadakis, Professor Martin Maxi, my group, and some collaborators from PFL in Germany and Yantan University. And with this, thank you so much, everyone, for your attention.
I think we started a couple minutes later, we can take one more questions. So, over time already, and we asked some questions already, but if you guys have the questions, we can take one more.
Yeah.
I have a very general question. So what would be the training of the for thinking or understanding?
Can you say that again?
I mean, what would be the training of this PIML? Is it overthinking or underthinking?
For pings?
Yeah.
For pings, usually it's a bit hard to overfit because you don't have true training data. So it would be hard to overfit in pings, because overfits you have when you're completely matching the training data, right? But in pings, you learn through an auxiliary value, which will be the residuals of your PD.
So it's underthinking.
It would be like, yeah, we can say, like, actually the right thing, like not overfitting or underfitting. Yeah.
Thanks, everyone. If you have more questions, we'll ask.